So we are in your chemistry, and we're in chapter 17, section 3, which is on nuclear reactions. And we got to the point that we're talking about the types of decay, and these types of decay emitting radiation. Now, to apply this, we need to know that radiation, of course, can be harmful, and it can be useful and it can be harmful. And we went over the different kinds of radiation. First of all, there's alpha decay and beta decay, and they produce radiation. And they can be alpha radiation with the alpha particles, they can be beta radiation with electrons, or they can be gamma rays that are emitted in the process of this too, or they can be neutron rays. Neutrons are where neutrons are split off from the nucleus and take off, into as rays, splitting other nucleuses. So, and that's the neutron rays. And we went over those already. But now we want to know, as the characteristics, we went over the characteristics, we want to know the penetrating ability of radiation. The 4 types of radiation we have discussed vary in their ability to penetrate matter. Some can go through things and others cannot. So how do we know? Let's find out. So here we have a picture here, penetrating ability of nuclear radiation. So you have the alpha particles. Alpha particles, as they take off, they're very heavy. They're helium, actually. They're 4 is their atomic weight, 2 protons and 2 neutrons. And they can, in the paper, if you just put paper in front of it, the paper stops them. They can't get through. So they don't pass through much. Now, beta particles are electrons, and they can pass through paper, but they can't pass through sheet metals. So they don't pass through the metals. Now, the gamma rays, of course, are the electromagnetic rays. They are very, very fast and high frequency, and they can pass through paper, they can pass through the sheet metal, but they're stopped by lead. The radiation stopped by lead. Neutrons, as they're passing through, they can pass through a lot. So here you have concrete. This is if you had a nuclear reactor, which they have for nuclear energy and nuclear bombs. Neutrons are splitting off and splitting other neutrons, which we're going to talk about in a little bit later. But these neutrons can go through notebook paper, they can go through metals, they can even go through lead, and they can almost go through concrete. They need a lot of concrete to stop them. So just to know. So here we know why the properties are. Here you have the alpha particle, heavy particle. It's a +2 charge. Its mass is heavy. It's 4. And it looks like a helium. And it can be stopped by a piece of paper because it's so big. Then we have beta, basically being that charge of electron, moderate, stopped by sheet metal. And gamma, here's the gamma. Gamma goes through all of these. The gamma are like photons or x-rays. So they can almost go through anything. When you're getting x-rays, how they put the lead on you. But anyway, basically, gamma rays are even higher frequency. So 99.9 are stopped by 5 inches of lead or 2 feet of concrete or 3 feet of packed earth or 5 feet of water. So this is when you have a nuclear plant, factory or something with nuclear energy. They have to make sure that they have all these. They have very packed with concrete, and with water and everything in the midst of a nuclear plant. With not just gamma ray, with gamma rays and the neutrons with the nuclear plant. So neutrons are easily penetrate several inches of lead, but can be stopped by several feet of water or concrete or neutrons. So these two are a lot of radiation, but basically gamma can be stopped by the lead stuff. Neutron penetrate through lead. Okay. So this picture here shows it all. So this is, we're going to go on to the next section actually. So it's getting into another aspect of decay. Now we're not going to talk about the radiation, but we're going to talk about something measuring half-lives. This is pretty important to know how to do this because every different element has a different half-life. You always hear about half-lives when you hear about dating and such like that. So Half-life are the rate of decay. That's what a half-life is. All radioactive substances that are unstable, have some are more unstable than others. They have different half-lives. So first of all, they were talking about, carbon. The carbon-14 has a half-life of thousands of years, 1,000 years or so before decaying. And bromine, 80, has a half-life of only a few minutes. So see how it can vary so much between different elements. It's ridiculous. So half-life is the decay rate of a substance and the length of time it takes for 1/2 the original substance to decay into a new substance. So half-life is just when it decays into a new substance. So half-life right here, the length of time it takes for 1/2 the original substance to decay into a new substance. So, okay, for example, you have 160 milligrams of a nuclide having a half-life of 10 years. So then after 10 years, you're going to half that one, only one, so you're going to half the next one. The rest would have changed into the, so anyway, just saying you're going to half each time, you're going to half it again. So it's almost like exponents. So after a 10-year period, 1/2 of the 40 milligrams will make 20 milligrams. We're going to later on describe that, so I'm not going to show you it. I'll show you when we have a question later on about it. In other words, the amount of nuclide remaining after each half-life is 1/2 of what you started with. So let's look at the picture here. So here are the half-lives of some. PO. See, we have PO half-life here. You can see half-life of selected nuclides. Here you have how many years half-life is in the midst, and each one, this one here is 1.64 times 10 to the negative fourth, so seconds. So, and here we have oxygen here with 8.7 times 10 to the negative 3 seconds. Bromine is in minutes. Magnesium, 21 hours half-life. Rn is 3.823 days, so 3 days half-life. Plutonium, or phosphorus is 14.3 days. And then on, and we have, as you see here, we have hydrogen is 12.26 years, selenium 28.1 years. On to, here's radon, Ra, 1,600 years. Carbon is 5,730 years half-life. We have potassium as 1.28 times 10 to the 9th years. These hardly decay at all. Uranium, 4.51 times 10 to the 9th years. This is, we're talking like, okay, these are not going to decay under the half-life's in decaying at that point. Although you can split uranium, that's for sure. So here is another picture of the half-lives on a chart of the years, the substance, taking how many milligrams of the substance and how they did the half-life, so 10 years, 20 years, 30 years. And so it says the substance remaining. So here you had, this is where it's showing this picture here of what they talked about. So if they have 80 milligrams as you go down, it's going to half that in a period of 10 years. The next 10 years, it's going to half 40. The next 10 years, it's going to half the 20. And then the next is going to half the 5. And next 10 years, it's going to half each time halving the one 10 years before is how you do that. So just to know how to do that, because you probably have a test question on that one, I'm telling you. So on to talking about the half-lives. Okay, to find out the amount of nuclide remaining after a given time, you have a given time. You find the number of half-lives contained in the given time period, and then you raise 1/2 or 0.5 to the power of this number, and multiply the original mass by the nucleotide, this and step. So anyway, so they have an example here. We'll go through it just really quick. Okay, here we have sodium, 24 of 11, has T 1/2, 15 hours. What is the mass? 1.6 grams. The sample remains after 60 hours. Okay, so determine how many half-lives have elapsed. 60, divided by the time is 1/2. 60 over 50. We're going to find it. This is what we want to find, our answer, what this is, the time. And so we have 60 hours divided by 15, so we have 4. So we need to go 4 half-lives have elapsed, and the mass of the sampling nucleotide must have halved 4 times. And so 1/2 with the exponent of 4 equals 1/16. So multiply the original mass of the sample by 1/16 to find the remaining. So 16 times 1/16 is going to be 0.10 grams of sodium remains after that time. So basically going back to this, just doing as they say to find it. Activity. Let's talk about the activity now. So activity. An important principle to remember is the half-life of a substance determines the intensity of the radiation it produces. What does that mean? So it means a substance with a very long half-life, such as uranium, takes 4.5 billion years to even get going, right? And it's very heavy. Decays so slowly that its radiation is easily manageable. For this reason, uranium-238 can be safely used in machines or tools or tanks or commercial airliners because it's not going to decay right away, right? A substance with a short half-life, such as cobalt-60, has a half-life of 5.3 years, and it produces radiation that is far more intense, thus potentially far more dangerous if handled incorrectly. So the half-life of a substance determines the intensity of the radiation. So if the half-life, when you think of if the half-life is longer, you're going to have, its radiation is going to be slow, easily managed. Now, if a half-life is short half-life, it produces radiation that is more intense. So it's opposite from the length of the half-life. So here we have cobalt, cesium, americium, so you have the half-life here is cobalt is a short half-life of 5.3. So we see here it's going to get more intense. Short half-lives are more intense. And so the half-life of cesium is 30 years. So it's less intense than cobalt, but it's more intense. And americium, which is, in the uranium group or whatever, it's going to basically practically unchanged for 432 years. So just seeing that. So just remember, the half-life of a substance determines the intensity, and the shorter the half-life, the more intense. And measuring activity here. So let's see, did I miss something here? No, okay. Okay, measuring activity of radioactive nuclear disintegration or decay. So you have the units that you're going to measure. So the SI unit is called the becquerel. The becquerel, after the scientist there, BQ, is defined as 1 nuclear disintegration per second. So if a substance undergoes 10,000 decays per second, it's going to be 10,000 becquerel. Because becquerel is a small unit, the older unit is called Curie, like Madame Curie, right? And it's SCI. This was used before. So either one of these are units to measure radioactiveness, the SI unit for the activity of radioactiveness, So 1 Curie is actually 37 billion disintegrations per second. And that's 1 Curie is 3.7 times 10 to the 10th. Both units can be used to refer to the amount of radioactive substance. So we're talking about the radioactive activity of it, right? So that's just the measuring devices, just to recognize those things. The radioactive decay series, okay? So, okay, this is like when you go into a series of reactions that are happening, calling them bombardment reactions, right? So this is when we're getting into the nuclear bomb stage when I think of bombardment, right? So when an unstable atom undergoes a nuclear decay, the new atom that results is called the daughter nuclide, right? Because it's changing into a new type of atom, but it's coming from the original. They call it the daughter, and this daughter may be very unstable too. So, and even more unstable. So the atoms will soon decay still another atom, and so on, and you'll go through this whole chain reaction. Another atom will decay, another one, another one. The result of this process is a long series of radioactive nuclides ending in a non-reactive state. They all want to get stable, so they're going to keep changing to a new one until they're at a stable condition. Such a chain of nuclides is a radioactive decay series. It's that reacting as a chain. So you may recall that all the elements of atomic number, which is Z, of 84 or higher are unstable to varying degrees. So if you have higher than 84, you're going to have a lot of heavy nucleuses are going to be unstable. And all of these elements gradually decay, forming radioactive decay series that end with stable isotopes of lead. Okay, so anyway, here we go. Let's go on to the next page here. Here we go. So radioactive decay. We have the thorium-232 series, the uranium-238 series, or the actinium-227 series. So these all are different series of decay of these three different types of elements. The actinium series is also known as the uranium-235 series. Very important because this series will end into, our atomic bombs, whatever. So we have the 238 uranium, actinium-227, and on to the uranium-235, which is that. And the thorium is the 232. They're all listed here. So the parent original reactants of these three states, and their decay and their decays involve either alpha or beta emission, whichever, and some have gamma rays and some don't have gamma rays. So these series are diagrammed here, so you can see. You'll see. Okay, we're going to look at the thorium. Let's look at. Okay, we started off with atomic number here as 92. We're going to decay the thorium. It's going to turn in. As we go down here, thorium turns in, and as it turns in to these, it decays more. It turns into another one. It goes as a chain reaction as it's decaying. Alpha decay is red, and beta decay happening too at the same times in some of these. See how they're decaying. So, but there's a series. First, thorium goes here, changes into PA. It goes down further, changes into this. And each time it goes down into a new changing. This is the actinium series in itself. So, okay. See this figure, how it's decaying. Just to know that it goes through a chain reaction of decay. So, lighter elements generally do not produce long decay series. So, but it's a generalization. Here we go. Let's see. Lighter elements generally do not produce long decay series, while super heavy elements typically have long decay series involving unusual nuclear reactions in addition to ordinary alpha and beta decay. So, super heavy. So bombardment reactions. So bombardment reactions. Stable nuclei do not normally undergo nuclear reactions, right? If it's stable, it's stable. But certain types of nuclear reactions can be induced into a stable nuclei if the nuclei are bombarded with other subatomic particles. So when you talk about this decay process, you're talking mainly about the decay process. Bombardment can cause this process to happen quicker in the midst of bombardment reactions. That's why I said this has to do with bombardment. Well, it kind of does and it kind of doesn't. So the activity is coming from the radioactive decay series. Radioactive emitting also comes from bombardment. And a lot of times it's caused by the bombardment. Let's just say that. So certain types of nuclear reactions can be induced. We talked about that. For example, if a sample of cobalt-59 is bombarded with neutrons from a nuclear reactor, some of the neutrons will be captured by cobalt-59 to form radioactive cobalt-60. So here's a picture, 59, and it comes a neutron, and then cobalt changes. In this instant, an induced nuclear reaction has occurred that left one changed form of cobalt into another. Left to itself, cobalt would never, ever have changed. You know, it had to be hit by a neutron bomb, right? A neutron that bombarded into its nucleus. Cobalt-60 for cancer treatment is produced in this manner. Nuclear reactions induced by pelting a sample with other particles is called bombardment reactions. So you're going to pelt them with neutrons. Actually, you can. There's other particles besides neutrons, you know, and there's, in fact, I'm going to name some of these particles. A number of other particles besides neutrons can be used to induce nuclear reactions, and these include deuterons, which are deuteriums, nuclei, which are hydrogen with two protons, a proton and a neutron, two atomic weights, deuterium, and ions of various other elements. Charged particles such as protons, alpha particles, and ionized atoms must have very high energies and thus high velocities to approach and react with the positive charged nucleus of the target. So anyway, neutrons are uncharged, so they're not repelled. So usually neutron bombardment is used where they bombard neutrons. Neutron radiation from specialized nuclear reactors is sometimes used to induce nuclear reactions on an industrial scale, like to produce electricity and power. You use a lot of neutron particle accelerators, or neutron accelerators, or neutron radiation. But also, on a smaller scale, they also use little particle accelerators, which I want to say that they're small but not huge factories, which use magnetic and electric fields to accelerate charged particles to energies of several million electron volts. So several million electron volts may be used to initiate these nuclear reactions. They use these in hospitals and such. In fact, let's go. I think they have a picture of one. So here we have in hospital cyclotron, and cyclotrons are used for PET scans, PET scans, and other medical procedures by bombarding particles. Here's a picture of them. So, and here is a large Hadron Collider, which is the world's largest particle accelerator. Remember I said, well, they're not like factories, but this one is like a factory. So it's the world's largest particle accelerator. You know, it's huge. So, although huge neutron atomic energy plants can be very huge. They're the whole factories, you know, in the midst. Much larger part, but that factory is a lot of different things. The coolants you'll see later on. We'll go over a nuclear energy factory and what these consist of in the next part of the chapter, so I'm not going to go over that. So These much larger particles can accelerate protons and other particles to billions or trillions of electron volts, enough to shatter protons and neutrons into their component parts or even to form new particles of excess energy. It's a particle accelerator. So, chemistry and actions, the uses of radionuclides. What are we using them for, in fact, So this is kind of important that we know, huh? Got the bombardment. Now, what do we use them for? Well, you can look right here. So if you see some useful radionuclide. Here's for americium. Americium is used for smoke detectors, environmental studies, industrial quality control. Californium, a lot of these are manufactured, of course, in the laboratory, I should say. Airport security, highway engineering, carbon, pharmaceutical research, archaeology with carbon-14, cancer, this is for cancer treatment, cesium, petroleum, energy, chromium, study of red blood cell studies, cobalt-60, sterilization of medical instruments, first aid supplies, food products, cancer treatment, PET scans with fluorine, luminous watches and exit signs and sights, dials, paints, biochemical studies. There's a lot for hydrogen, tritium. Iodine, treatment for thyroid disorders, iodine 31. So these are the half-lives. And PET scans with the oxygen and the nitrogen and the rubidium. So all these things used for testing of aircraft and pipelines. So you can see basically some useful radioactive nuclides that so in the midst. So bombardment reactions can be used to produce a tremendous variety of artificial isotopes that are not found in nature. These radionuclides have led to great studies in almost every area of science. A few new radionuclides and their uses are given below. So here they are, used for good uses. So all the elements beyond uranium are called transuranium elements. They all have been artificially prepared by bombardment reactions, and some of them can occur in very trace amounts, but mostly they're manufactured. For example, the bombardment of uranium-238 by neutron produces uranium-239, which then immediately goes under beta decay to form neptunium. Here we have the picture of the equation, how it goes through the decay. And then in a few more hours, it only takes a few hours, neptunium goes through another beta decay to form plutonium. Plutonium is what we always hear. So even nuclear bombs and everything, you always hear the word uranium and plutonium because uranium changes into plutonium. Some of the heaviest transuranium elements have been produced by bombardment reactions using fairly massive particles such as calcium, So anyway, we see can you imagine them bombarding with calcium? That's ridiculous, but they do. So here we go. Here's the selective transuranium elements: plutonium, americium, curium, californium. See the unusual names too? They all are basically artificially prepared in the laboratory. I was going to say artificial manufacture, but it's artificially prepared in a laboratory situation. And here's the reaction, how they do it. Okay. I'm going to go through this really quickly, maybe a little bit of overtime, but this is the concept, the chapter review, concept review here. It says, name 3 types of nuclear decay and write one for each. Okay, so what was the nuclear decay? You remember? Alpha, beta, decay, and gamma, or neutron. Actually, gamma and neutron come from alpha, beta, or gamma. So, and it says write one symbol. I hope you know that alpha symbol is like the Greek alpha sign, kind of like that. The beta symbol looks like a Greek B, and the gamma is like a Y. So, which type of radiation consists, alpha, beta, or gamma, consists of high-speed electrons. What would you say right away? Which are the electrons? Beta, right? Consists of electromagnetic waves. Gamma wave are electromagnetic waves. Consists of high-speed helium ions. Alpha are helium ions. Reduces atomic number by 2 and mass number by 4. Alpha. Alpha is the big particle. Increases the atomic number. Beta. Remember, one of the neutrons turned into a proton? That one. And so does not affect atomic number or atomic mass. Gamma doesn't affect it at all. Gamma rays are gamma rays. Is stopped by a sheet of paper. Alpha are so big that they're stopped by a sheet of paper. So that was easy. Name one use for each of alpha and beta and gamma and neutron radiations. So remember alpha? I would remember the smoke detector, the alpha big the particles actually are when the smoke comes in and it blocks, the smoke blocks off, it goes off. So I would say a smoke detector would be a good one. Beta, those beta watches that light up, was one. Gamma rays, they can use it for the PET scans too. Gamma treat cancer. They treat cancer with gamma rays. Neutron radiation, you can use neutron radiation in the midst of a lot of different things, cancer treatment and everything else, but also neutron radiation. I always think of neutron factories of electricity, making by fission process of neutrons. So what is the half-life of a radioactive substance? So what was the half-life is the decay rate of a substance. The length of time it takes for 1/2 the original substance to decay into a new substance. Those are half-lives. Number 5, what is the activity of radioactive substance? The amount of decay occurring in the radioactive substance. The activity, when you do it, thinking of the activity, you're thinking of the decay. So you're thinking of radioactive substance. What is the activity? We went over that. I did a whole thing on radioactive substance. But a lot of the decay is as they become radioactive, they're decaying. What is the radioactive decay series? So is going through the many types of radioactive decay, one after another. One decays to another, and then right away it decays to another and decays to another, right? They change. The radioactive substance, when it decays, changes to a new substance. Let's just say that. So on to number 7. How can a particle accelerators be used to induce nuclear reactions that would not otherwise occur? So a particle accelerator is used by bombardment of particles, which can be neutrons or they can be whole particles. It could be protons or they could be alpha particle, whatever they use as particles. So a particle accelerator is used as bombarding other nucleuses. So let's see here. Let's do this one here. I'm not going to go on to do this one here, but I want to do this one. If you started with 32 grams of a substance having a half-life of 1 year, how much would the original substance be in 2 years or after 4 years? Okay, after 1 year, you'd want to, the half-life is only 1 year. So after 1 year, it'd be half of 32, which is 16. That'd be 1 year. So after 2 years, it'd be half of 16. So what's half of 16? Half of 16 after 2 years, it would be 8. And so after 3 years, what would it be? It would be half of 8 would be 4 after 3 years. So after 2 years, how much would it be? After 2 years, it's, basically after 2 years, it would be half of 4, which would be 2. So, or after 4 years. I'm sorry. Let's start again. Go through it so I can make sure I have it right. So you have 32 grams are going to be halved every year. So after 1 year of half of it, it's going to be 16. So after 2 years of half of it, it's going to be half of 16 is 8. And after 3 years, which is not missing here, it's missing, it's going to be half of 8, which is 4. So after 4 years, it's going to be half of 4, which is going to be 2. So this would be 2 years. Okay, let's go up. We're going to stop there.